Okay, everyone. Until now, I would say the course has had two plot lines. One plot line is okay, we do functional programming in Galena, and okay, it's weird, but you've gotten used to it. Okay, maybe it's kind of cool, getting good at recursion, feeling good about it. That's the A plot. And then the B plot is like, oh, there's all these proof things, and okay, Cock's pretty weird, but like these tactics seem like a way to do cool proofs, and like you're starting to follow along, and okay, induction, that's cool, all these propositions, that's all neat. The A and B plots are going to meet. So it turns out you can write programs with propositions, right? So you can write programs that say generate propositions. Um, the example I want to give for that is a program that determines whether or not a given element is in a list. So you've already seen programs that do stuff like that, functions like member or functions like lookup and things like that. So you've written membership tests. Like, what do I mean? We're going to write a program that generates a proposition that will be true, will be provable, uh, only if something is in the list, right? And we're going to do it by writing a Galena program that is returning a proposition. So this is stage one of A and B plots mixing. Stage two will be day 16 when we learn about inductive propositions, and we sort of start to really see that, like, oh, there's this whole other way of defining propositions that sort of lets us really like have multiple ways of coming at these propositional ideas. So let's start with this one. Um, what does it mean to say that an element X occurs in a list L? Well, if L is the empty list, then it doesn't, right? Like it's wrong, right? No, there's nothing in the empty list, so like it is not the case that any X is in there. If it's not empty, then well, if L has the form X prime cons L prime, right? L looks like this, and you have some X, then X occurs in L if either it's equal to X prime, right, the head of the list, or it occurs somewhere in L prime. So let's write a recursive function that says this, right? So fixed point. I'm writing this with a capital letter I, which is just part of like a thing where like types for data are going to have lowercase names, and then types for propositions are going to have uppercase initial letters. They'll be capitalized. So in for some type A says, okay, well, X is a value of type A, L is a list of A's, and we're going to return a prop. We're going to return a proposition. And that proposition will be something that will hold when something is in the list. Okay, what do I mean by that? Well, let's look at L. If L is empty, then false. Right? If L is empty, then it is not the case that X is in the list. So it'll be unprovable. If L is a concel, X prime cons L prime, then well, when is X in L? When either X is equal to X prime, it's the head of the list, or you can find X later in the list. So this is like probably like an uncomfortable moment. It's like when you have like two good friends and you don't think that they knew each other, and it turns out that they're also good friends. And like on the one hand, it's like great, now all three of you are friends, but on the other hand, it's like, how didn't you hear about this? Like why didn't they ever mention each other to you? Like what's going on, right? It's like a confusing moment. So like take a deep breath. This is just an ordinary recursive function. The only thing that's new here is that we've decided to return prop as opposed to something else. Everything else is a very conventional function like we might write. So like, okay, and we're returning props appropriately. So what this is this is a function that given a value and a list and an given two inputs, will compute a proposition for us, right? We're programming with propositions. Okay, let's do some concrete examples. So first, let's look at just proving that 4 is in this list. So let's see what happens. If I simple, Cock can run this program to the end. Let's take a second to look at that. So when I said simple, I said, hey, Cock, my current goal is this proposition that 4 is in the list 1, 2, 3, 4, 5. Could you tell me what that means? And like, we've never simpled a propositional goal before. Like, we've done equals to like run programs, but now we're saying, right, yeah, my goal is a proposition and I want you to run it because it computes something concrete. And let's see what it produced, right? It produced a series of ORs, right? Which makes sense. It's going to be a bunch of these ORs from the recursive case. And eventually we get to the base case and we just return false. So what does it mean to have 4 be in the list 1, 2, 3, 5? 1, 2, 3, 4, 5? Well, it's 1 is either equal to 4, or 2 is equal to 4, or 3 is equal to 4, or 4 is equal to 4. That's the one we want. Or 5 is equal to 4, or false. Interesting. So like we were able to just say, okay, this is the proposition we want to prove, and then that computes to some interesting proposition we care about. Okay, so how do we prove this? Well, these are a bunch of ORs. So like right, right, right. I failed out of the boot camp. I just did too many rights. Left. Okay, perfect. Now, as usual, you can make a wrong turn. You keep going right. Yeah, I say you can't go wrong going right, but you absolutely can, right? So, as usual, you gotta do it correctly. Dare I say, do it right? Um, but it just works that way. So far, it's like okay, it's a program that produces a proposition. Neat. Let's see how you might use it. So let's look at this example. Intros H. Whoops. Just kidding. Intros NH. So let's see. We have a natural number n. We know n is in the list 2, 4, and we need to show there exists some n prime such that n equals 2 times n prime. Okay, well, that's fine. Simple in H. This in n24 is really saying, look, n is either the first thing in the list or the next thing in the list, or you're out of luck. Okay, cool. So destruct H as HN2 or HN4 or contra. Okay, let's see. In HN2, we're in the case where 2 is equal to n. Okay, well, now we need to find that there exists some n prime such that n equals 2 times n. Okay, great. Exists 1, reflexivity. Right. Oh my goodness. The other direction, please. Thank you. Wow. Okay. 4 equals n, exists n prime, n equals 2 times n. Okay, great. That's going to be 2. Great. Huh, contra in an empty list. Okay, well. Oh! Ha, great. Beautiful. Okay, so how did we use this in? Well, we asked Coq to simplify it. Here I just destructed on it without simplifying, but you could simplify first. We asked Coq to like, okay, what are the cases? And then we just enumerated the cases. Right. So in a certain sense, you can think of in as kind of a macro, right? It's saying, take this thing and then turn it into this thing. Now, it's not exactly a macro because we can prove much more interesting things. Here's a lemma relating in to the map function. Let's see what it says. It says if some x is in the list L, then f of x will be in the list of mapping the function f over L. Right? Kind of makes sense. Map is structure preserving. So, if you found x in some position in L, then f of x has to be there somewhere. All right, let's see how it goes. Okay. Let types A and B be given such that f is a function A arrow B, L is a list of A's, and x is in A. We want to prove that if x is in L, then f of x is in map f of L. We'll go by induction on L. Now, why induction on L? Well, look, in the proposition we're trying to prove, or the program we're trying to reason about, depending on your perspective, is recursive on L. So that's going to be the thing we want to do induction on. Okay. Let's go. Okay, the first case is when x is empty. So that is contradictory. The second case is when, okay, x is in the list, x prime cons L prime. We need to show that f of x is in the list, map f over x prime cons L prime. Okay, simplify, we can see these ors. This is maybe not the nicest to simplify right away. So let's just say, okay, look, by cases on this in. That's maybe even still not clear enough. Let's be clear. Suppose that x is in here. If we simplify in H, we can see, oh, that's really saying either x is equal to x prime or x is in L prime. So destruct H as H or H. H was a good name at first, and we'll stick with it. Okay, the first case is, yes, x was the head of the list. So now we need to see that f of x is going to be in this list on the right. Why? Well, it's going to be here, right? Let's see something. Simplify. Either we need to know that f of x prime equals f of x, or we need to know that f of x is somewhere in the tail. But look, we know x prime is equal to x. So we could say rewrite by h, and now we just need to show f of x equals f of x. Okay, so good. We're good to go on the left. Alternatively, maybe we know that x is somewhere in the tail of the list. Okay, if we simplify, we'll see, like, look, we have a choice here to prove this in. We can either show that we're the thing in the head of the list, or we're somewhere in map FL prime. But if you look at our IH, that one looks pretty good. So we'll go right, and we'll say, well, look, the IH says exactly what we need. All we need to do is show the IH's precondition, that in XL prime, but that's exactly what we knew. Okay. So I have some lemmas for you to do working with in and stuff like this. We're going to see yet another way to do interesting reasoning with propositions in day 16, but this is sort of, step one of merging our understandings of programs and propositions. I want to conclude by just making a tiny remark. We've seen quite a litany of tactics. It's a lot. We're going to get just a few more tomorrow, and then we're done. I promise. No more tactics after that. After that, we're going to do some case studies. After tomorrow, we'll have learned the last important thing we need to be able to do sort of basically all the math that we're going to care about in Coq. And then after, I think, 2 days of those case studies, we'll finally move on and start doing informal proof, start seeing how to take the understanding that we've developed in Coq and apply it to doing reasoning just on paper. So great. We're a little bit over halfway through our incredible proof journey. I hope you're having fun. I know I am. Talk to you soon.